Hello everybody, this is Dr. Sankar Bose from Presidency University, Kolkata, and today we will be discussing about a topic on quantitative geothermobarometry and pressure temperature time paths. So, today's discussion is based on what is known as geothermometry and geobarometry and how we use those things in metamorphic petrology, and then we will be dealing with problems how to reconstruct these geothermometers and geobarometers and how to use them judiciously in natural rock systems. And finally, we will be dealing with the results of geothermometry and geobarometry in deducing the pressure temperature paths, which will have infinite importance in reconstructing the tectonic setting of any metamorphic rocks. To begin with, I shall start with the fundamental question of what is geothermometry or geobarometry. Now, metamorphic petrologists over the years, they were pondering about the idea of metamorphism, what are the different factors responsible for metamorphic process, how much intense these factors were. Initially, people used to go to field work and describe rocks, metamorphic rocks particularly, as high grade rocks, low grade rocks in this fashion. The question is how high or how low? For that you need the absolute values, and that absolute values can be determined using the principle of geothermometry and geobarometry. So, my discussion will be specifically centered on what are the concepts behind geothermometry and barometry, the thermodynamic background behind this topic. Then we will be discussing about some very well known thermometric and barometric formulations, how they work on natural rocks, what are the different precautions that we have to take during applying of these thermometers and barometers, and what are the advancements that we have made over the years. So, let us begin our class today. So, initially I want to explain the basic meaning of this term geothermometry and geobarometry. What is a geothermometer, or what is actually geothermometry? It's a thermometry, means it's a measurement of temperature, but it's not like what we use for measuring our fever or something like that. So, it's basically geothermometry is measurement of temperature of metamorphism or temperature of any igneous process using the equilibrium mineral assemblage in a rock. So, it's basically a mineral assemblage and a reaction which is in equilibrium state in a rock. Similarly, geobarometry is the measurement of pressure. It's a metamorphic rock, then it's metamorphic pressure, or if it's an igneous rock, it's a igneous pressure of the magmatic body. So, measurement of pressure similarly using a mineralogical reaction, which means it's a stable mineralogical reaction that is in equilibrium. So, both geothermometers and geobarometers, they are mineral reactions that is they are in equilibrium state, and we have to document those reactions from natural rocks. Then we can use the principle of geothermometry and geobarometry. So, to begin with, how to formulate these equations, we have to go back a little bit, and you have to understand the basic geochemical thermodynamics. In a geochemical system, a phase and its free energy of any phase can be represented by the term that is G, which is Gibbs free energy, is equal to the internal energy, that is E, minus temperature and its entropy, that is G is equal to E minus Ts plus its pressure and molar volume. So, the free energy of any system, free energy means I am talking about Gibbs free energy. Gibbs free energy of any phase in a system is a function of internal energy, the temperature of that point of that situation, and the pressure and volume, molar volume of the rock. So, G is equal to E minus Ts plus PV. Take any solid reaction, say A plus B giving C plus D. Suppose these minerals A, B, C and D are in chemical or textural equilibrium. In that case, the total free energy of the system of the reaction is given as delta G is equal to delta H at 1 T minus T delta S plus P delta V plus R T log natural K. This K is known as the distribution coefficient and is given by the activity of the product phases divided by the activity of the reactant phases. For any equilibrium reactions, this K is also expressed as Kd. Now, in this equation you can see what are the known parameters. Parameters like H, that is the enthalpy, parameters like entropy S, and parameters like V, that is the molar Gibbs free energy. These values are known from any thermodynamic data table, and if the reaction is in equilibrium conditions, then delta G becomes 0. So, we can apply this equation to solve the values of temperature and pressure, these two unknown parameters. So, what we need is to calculate the value of K, because all other parameters are known, and this K value is dependent on the activity of the participating phases, any species in the participating phases, and this activity is a function of mole fraction, and you can express activity is A is equal to x into gamma, that is x is the mole fraction and gamma is the activity coefficient. For this kind of reaction where the participating phases are showing ideal solid solution behavior, in that case gamma becomes 1 and activity becomes mole fraction. So, you can express K as mole fraction, product of mole fractions, and mole fractions can easily be calculated from the mineral chemical data. So, we need to get the mineral chemical data of the phases that are in equilibrium. So, that parameter is needed. Now, if we get the value of K, then we have left with two parameters, two unknown variables, that is pressure and temperature for one reaction. So, if the left hand side becomes 0, you have two variables and only one equation, so it cannot be solved. So, unless you know the value of one variable, you cannot solve it. So, we need a value of P for solving T, or otherwise we need a value of T to solving P. So, we need a specific reactions which are independent of pressure. So, whatever value of P you get in this equation, the value of T will be different. So, we use a very good barometer where the value of P can be calculated using any given value of temperature. Ideally speaking, in that case the reaction of that A plus B giving C plus D, this reaction will have a very flat pressure temperature slope, PT slope. On the other hand, if we want to calculate the value of temperature, we can put any value of pressure to get the temperature value. In that case, ideally speaking, the equation A plus B giving C plus D should be very steep. So, this is the principle of thermometry and barometry. We have to find out an equation where which is insensitive of pressure, that is a very good thermometer, and we have to find out an equation where which is insensitive to temperature, which will be a very good barometer. So, as I told you that a very good thermometer should have a very steep dp/dt slope. We know from the Clapeyron's equation that dp/dt is given by del S by del V. So, for a very good thermometer, it should have very high delta S, that means high change in entropy, and very small or insignificant delta V. This should be very sensitive to temperature and not very much sensitive to pressure. So, what could be an ideal equation or ideal reaction that should have very high delta S and very low delta V? Ideally speaking, ion exchange equations or cation exchange equilibria, say for example, the equilibria between pyroxene and garnet or biotite and garnet, where iron and magnesium, they change their position in different sites of iron and between garnet and pyroxene or garnet or biotite, should be considered an ideal geothermometer, because the transformation of iron rich biotite to magnesium rich biotite vis-a-vis magnesium garnet to iron rich garnet, that needs a lot of change in entropy. So, the entropy change is very high, delta S, and since no breakdown of any minerals are required, so the molar volume change will be minimal. So, those cation exchange equilibria, which normally occur in metamorphic rocks of different bulk composition, they should be considered ideal as thermometers, geothermometers. So, these cation exchange thermometers or ion exchange thermometers are very good, but there are two different categories of ion exchange thermometers. One is called the intracrystalline cation exchange thermometers. That means the cations, say for example Fe and Mg, they can exchange positions in the different crystal lattices within a single mineral. For example, say pyroxene, orthopyroxene, it has two octahedral sites, M1 site and M2 sites, and we know that iron and magnesium, they do not partition equally in these two sites. So, their partitioning in the M1 and M2 sites depend on the temperature conditions. So, calculating the amount of iron and magnesium in M1 and M2 sites, we can calculate the temperature of this partitioning. So, this is called intracrystalline ion exchange thermometer. The other one, that is the intercrystalline ion exchange thermometer, is very common in metamorphic rocks. We can use it in different kinds of metamorphic rocks, where the elements, ions, cations particularly Fe and Mg for example, can be exchanged between two different minerals, that is intercrystalline. So, as I told you, take an example of garnet and biotite, where magnesium garnet can react with iron rich biotite to produce iron rich garnet and magnesium biotite. So, iron from the biotite directly goes to the sites of the garnet grain, and magnesium from garnet can go to the octahedral sites of the biotite grain. So, this change of elements between two minerals is temperature driven process, and when the temperature the distribution of these elements can be measured at equilibrium conditions. So, we can get the value of Kd, and we apply this Kd value in the equation to get the temperature estimate. There are other methods as well apart from this. Normally what we use cation exchange thermometers, say we can use isotope thermometers or isotope thermometry, that is we can similar to the cation slide, though the isotopes of different elements can be exchange for any mineral, for example oxygen isotope. We can measure the oxygen isotope values, and this distribution of isotopes is also a function of temperature. Otherwise, we can also use solvus thermometers. What is that? Solvus thermometer is the temperature composition diagram where a mineral show mixing of different components at high temperature which unmixes at low temperature. So, this mixing and unmixing mechanism can be used to get the temperature values. I will come to that later. There are new methods appearing in the literature of metamorphic petrology, say for example trace element thermometry. It is a new addition. We can see that the trace elements normally they form very small accessory minerals, but these trace elements can be used as a thermometer because their distribution in major silicates and oxide minerals can be temperature driven process. The most common example is the zirconium distribution in rutile or titanium distribution in zircon. These two minerals, zircon and rutile, they are very common accessory minerals in many metamorphic rocks, and when there is no other methods that could be applied to any rock, these trace element thermometers can give very reliable temperature values. And there is another separate class of thermometers, what we call fossil thermometers or fossil textures thermometer. These are like normally we consider the fossils, that means the relics of some processes. For example, take the case of pyroxene exsolution. So, if we have a pyroxene exsolution texture in metamorphic rocks, say a metamorphic orthopyroxene contains exsolved lamellae or blobs of clinopyroxene. Now, this exsolution of pyroxene normally occurs at very high temperature, say temperature higher than 900 degrees centigrade. So, if these textures are preserved in any metamorphic rocks, and if we get any temperature much below 900 degrees centigrade, these results are spurious, because if you have those textures in the pyroxene grains, it automatically signifies the temperature of metamorphism should be as high as 900 degrees centigrade. So, these are considered as very reliable indicator of high temperature metamorphic process. Here is an illustration how we can use solvus thermometry in metamorphic rocks. In the first left hand corner figure, this is a natural example of feldspar crystals found in Antarctic rocks. Now, these feldspar grains, you can see this P is plagioclase and this is quartz and this is the feldspar grain. This feldspar grain is of course intergrowth feldspar, that is the perthite feldspar, and this M stands for mesoperthite. That means in this case the host and the guest proportion is almost similar. Now, these perthite grains, we can, if you can analyze this perthite grain and calculate the mole percent of different components, we can use as a thermometer. A very simple explanation is in this diagram, where this is a binary diagram. In the left hand side, this is albite, this is orthoclase. The composition varies in this along this line, and this is the temperature axis. So, this is basically a Tx diagram, and in this diagram this is the solvus line, below which two feldspar occur as two phases, and over which this is the alkali feldspar solid solution phase. So, anything above this will be a single phase. So, any solid solution of feldspar, if it cools down and touches any point of this solvus, it will be unmixed into two components, one rich in albite component and another rich in orthoclase components, and you will see the perthitic textures to form. So, if we integrate the amount of albite component and if you integrate the amount of orthoclase component, we will get the bulk composition somewhere here, and if we take this line further upwards, it will touch the point A, and this A point gives some connotation about the temperature. So, the temperature of unmixing is somewhere close to say 600 degrees centigrade. So, if we apply this in thermometry, then we can, this will make our task easier if we can calculate the volume percent of albite and orthoclase, and we plot this volume percent in this diagram, we can have the idea of what temperature is indicated. This is for two feldspar diagram, but natural feldspars in natural rocks, they occur as three different components, that is the albite, orthoclase and anorthite components. So, from the same rocks, if we calculate the amount of different components, anorthite, albite and orthoclase, these are the values, integrated values here, and you can see that these fall on the line of different isotherms. So, this is 1100 degree centigrade isotherm, this is 1000 degree isotherm, this is 900 degree isotherm. So, these values, these compositions are plotted on these isotherms, indicate these are the temperature of unmixing. So, this is very uniquely done, and you can, even in case of Antarctic rocks, very high temperature of metamorphism could be estimated using this method. But remember that this method only estimates the temperature of unmixing, whereas the metamorphic temperature could be more than that. So, that is one limitation that I will definitely discuss later. So, after this discussion on solvus thermometers, let us look at what are actually taking place in natural rocks. So, what we use for in metamorphic petrology, there are some examples, say for example, the garnet orthopyroxene thermometers is formulated by Lee and Ganguly. You can see the equation here, T is given by some factors, and if you put the value of pressure in it and you can calculate the value of Kd, you can get the value of temperature. Similarly, the garnet clinopyroxene thermometers of Ravna, this is having a little bit complex equation, but again you want to get the value of pressure and you have to calculate the value of Kd, and then you will get the temperature value. Now, this is the formulation of garnet biotite thermometer. It is formulated by very long back by Ferry and Spear 1978. They made some calorimetric measurements and calculated the value of ln k versus 1 by T, and they formulated this equation of the straight line given by ln Kd equals to minus 2108 by T plus 0.781. This is widely used as the garnet biotite geothermometer of Ferry and Spear, and many people after that they calculated the same equation, same reaction using different components, different chemistries of minerals, and they have different values. Now, this is a formulation of the garnet aluminosilicate silica plagioclase geobarometers experimentally deduced by Casual and Newton in a similar fashion. This is an experimentally calibrated curve, and using this curve they also formulated the barometric equation. So, what we use that in we use same mineral assemblages in different metamorphic rocks, calculate the K values and putting temperature in reactions, we get the pressure estimates. Now, for any specific metamorphic terrain, we have lot of different minerals, and using those mineral equilibria we can formulate the pressure and temperature values, calculate values, and in this diagram I am showing you what happens when we use different formulations for the same set of minerals. You can see the temperature axis we have different, along the pressure axis we have different thermometric calculations. The garnet biotite thermometers many people have done different calibrations and therefore have different formula, and that extends from say temperature 400 to almost 550 degree centigrade, and the same garnet aluminosilicate plagioclase quartz barometer pressure values ranges from say 2 kilobar to about 8 kilobar. Now, these values differ because each of these workers use different premises. So, the values differ. So, the actual pressure temperature conditions of any rock should be plotted in the blue region in this diagram. Now, as we know that you can use pressure temperature conditions of any given mineral pair or mineral assemblage, then the question is how do we use this pressure temperature value for a dynamic system like metamorphic process. We actually can calculate different pressure temperature conditions for the same rock undergoing a metamorphic process. That is, we are talking about the concept of metamorphic pressure temperature path. So, we can actually construct pressure temperature evolution path using geothermobarometric results. This is an example of a garnet plagioclase quartz biotite aluminosilicate assemblage, where we can calculate you can see the garnet grains, they have different zoning pattern. The almandine and pyrope content, that is the Fe and Mg contents are showing depression at the center, and the manganese and calcium contents are having very high conditions at the core. That is, the garnet as it was growing, it was losing the manganese and calcium and gaining iron and magnesium, that is growth zoning, and the plagioclase compositions is associated with the garnet, and you can correlate the plagioclase anorthite content with the different plagioclase inclusions within these garnet grains. We can assume that each of these plagioclase grains associated with garnet was in equilibrium, and we can calculate each pressure temperature, in this case the pressure values, and using the garnet biotite pair in a similar fashion we can calculate temperature values, and using the continuous pressure temperature conditions from these values we can construct a PT path like. So, in this case using the same conditions, the core composition of the garnet and biotite gives the temperature around 600 degree centigrade, and the garnet plagioclase assemblage along with quartz and aluminosilicate gives a pressure around say 9 kilobar, and the rim composition of garnet which equilibrated with garnet as well as plagioclase give a pressure value of around say 5 kilobar and the temperature value around 600. So, this interior is somewhere in between the core and rim, and we get also the values of pressure and temperature of these conditions. So, you actually have 3 points through which the pressure temperature path moves along this system. So, in this diagram we can see how quantitative pressure temperature estimates give us very robust estimate of the pressure temperature paths. But this is very important that to get the actual values of pressure temperature, otherwise if we just assume some values and draw the pressure temperature path without getting the actual data, that this may lead to disastrous conclusion that I will discuss again. We have seen that pressure temperature estimates give us very robust tool to infer about the pressure temperature paths, but we must be very careful about what we are getting. The data should be checked properly whether we are getting right data or not. So, that means we have to deal with the different errors that may come during analysis of our temperature and pressure conditions. So, what are the different sources? We have many sources actually. For example, the basic problem that normally occurs is that our geochemical thermodynamics which is the basis of all our calculations. The delta G becomes 0 only at equilibrium. So, when we are applying this the principles of geochemical thermodynamics, we tacitly assume that the system is in equilibrium, but in natural rocks it is very difficult to find out or establish whether the rock is in equilibrium or not. So, we need very rigorous analysis of mineral textures and chemistries to be sure that the rock, the part of this system under my observation or our observation is actually equilibrium. Unless we can be sure of that, it is very difficult to use the principles of thermometry and barometry. There are other errors like the error in the sensitivity of formulations. Some thermometers are formulated on the basis of some certain chemical constraints. For example, Ferry and Spear's garnet biotite thermometer did not consider the effect of manganese in garnet or titanium in biotite. So, if we use in a manganese and titanium bearing system, the values that we will be getting should be erroneous. So, that you have to take into account. There are other errors like say the microprobe data we get for any oxides and silicates. The iron content is given as iron oxide without mentioning how much iron 2 plus or iron 3 plus is there. Unless we get that, the Kd values becomes meaningless, because if iron 3 is there, so the Kd value, the magnesium part will automatically increase. So, the temperature values may differ, and mineral zoning is also another factor. Mineral zoning, if it is present in a rock, that means in a mineral, that means it is not in equilibrium, but you have to consider that mineral zoning is a continuous process, and we can assume that if the zoning takes place, then this is in equilibrium for a long time with different mineral. Most of the formulations they use different thermodynamic database. Now, this thermodynamics database we use uncorrected values, volume corrections are not done for many phases. So, these thermodynamic databases, if we use them, they can lead to different errors, and also in some cases, say for example, the garnet biotite thermometer is useful for a temperature range 400 to 800 degrees centigrade. That is where the original experiment was done. So, if we use this thermometer for any rock which underwent temperature of metamorphism below 400 or over 800, and if we get those data, those are definitely not the correct one. And finally, we have to be considered about the blocking effect, that is the problem of diffusion. If this FeMg or other elements, they change their places due to diffusion process, and when the rock attains high temperature conditions during metamorphism, after cooling from the high temperature retrogression, the elements that moved from one place to another place, they come back due to cooling back reaction, and that causes a lot of disturbance in the Kd values, because the Kd values will always be changed, and at the temperature where this movement actually closes is called the blocking temperature. So, any normal geothermometers, exchange geothermometers, they suffer this problem. The temperature values we get is very close to blocking temperature, but we can extrapolate, we can actually overcome this problem using convergence technique. In this diagram, I am showing the nature of PT path that can be constructed using the geothermobarometric data. As you can see in this diagram, a PT path having point from A to, this is pressure maximum pressure, then follows the heating path, and finally retrogression and cooling. Now, this kind of PT path can be reconstructed from the geothermobarometric data. A complete reconstruction will give this kind of picture. Another kind of pressure temperature path we constructed, the sense of movement of the pressure temperature path is slightly different. In this case, the temperature increases fast, reaching the maximum values, followed by a cooling path. Now, this type of pressure temperature path where pressure reaches the maximum value initially, followed by heating and cooling and decompression, is known as clockwise PT path. On the other hand, the other variety where temperature maximum reaches earlier than the pressure condition is known as the anti-clockwise path. This clockwise and anti-clockwise, these terms are used to show the movement direction of the path, PT path. Now, these clockwise and anti-clockwise PT paths have very grave tectonic importance. That means, this kind of clockwise PT path can be formed in only specific tectonic environments, tectonic settings. On the other hand, anti-clockwise path can be formed the other kind of tectonic settings, that also is very specific. So, if we construct the PT path in a very robust manner, rigorous manner, then we can easily comment on the tectonic setting. Otherwise, it will be problematic because these clockwise and anti-clockwise sense of paths, it depends on the nature of prograde path. Unless this prograde section is not constructed in a very precise manner, you cannot comment whether this is a clockwise or anti-clockwise path, because this section and these sections look very similar. But if you have this part well constructed, then you can say that this is a clockwise path. So, prograde path construction, reconstruction is very important. Now, with the time, people use lot of geothermometers and barometers to delineate the actual pressure temperature conditions. In the last few decades, there has been a huge change in the computation techniques with the advent of computers and different softwares. So, nowadays we can calculate pressure temperature conditions using different softwares, but there was one problem. All the cases we use univariate reactions that are plotted in PT space, and we calculate the temperature and pressure, we construct pressure temperature paths. But in normal cases, natural cases, univariate reactions are seldom found in natural rocks. So, there was a problem. So, now softwares are so designed that you can actually calculate divariant and trivariant mineral equilibrium using softwares. In this diagram, this diagram is a phase diagram calculated using a software called Perplex. Here, this is also a pressure temperature diagram, but this diagram is constructed on a specific bulk composition. Okay? And in this diagram, all the minerals are shown in different stability fields. You can see each field is shown in different color code. Say for example, this is white, this white field, and this is gray, and this is still gray. So, these different color codes indicate different degrees of freedom, and these are definitely divariant and more they have higher variance. So, in this diagram you can actually calculate the pressure temperature values from these phase diagrams using this phase diagram and construct the PT path here, that is giving you much more reliable sensor of pressure temperature evolution of the rock. Now, this approach is called phase diagram modeling, or sometimes called pseudo section modeling. Now, this is very popular nowadays because of its flexibility. We can use different database, we can actually design our own system, we do not have to rely on the model systems. So, this is very popular. Using these diagrams, this kind of diagram, we can use a variety of metamorphic rocks and their pressure temperature histories. Now, the problem in this case that even if you have a phase diagram, in that the precise location of the peak metamorphic condition, the pressure temperature conditions is very difficult to get, because all of these divariant fields have wide pressure temperature intervals. So, what is the location of the actual highest pressure temperature conditions? Now, this was a problem that was also addressed by the phase diagram calculation, where we can use compositional isoplates. That is, suppose a garnet has 4 different components: almandine, pyrope, grossular and spessartine. Suppose we take the grossular content or say pyrope content and their distribution in the garnet stability field. In the using this, you can have this pyrope contents in garnet, they can be plotted in the stability field of garnet. This 38 means 38%, 40 means 40% like that, and using this along with another mineral, say plagioclase here in this diagram, their albite content. Okay. You can calculate the albite content of plagioclase and they can plot as isoplates here, and when you get the actual peak metamorphic mineral assemblage, you can calculate the albite content in plagioclase and pyrope content in garnet, and using these two isoplates meet somewhere here. Now, this is the highest pressure temperature conditions for this given rock. So, this is where the peak metamorphism is situated here. So, actually we can use these isoplates to mark the highest pressure temperature conditions, followed by the changes in the compositions. We can draw the pressure temperature path like this. So, using these values we can actually calculate the construct the pressure temperature diagram. Similar can be used of in case of mineral modes. These software they have a lot of flexibility and they can be used in according to our choices. So, friends, we have reached the end of this session, and before we go back, I will conclude this session with some points that we have made in this classroom. First of all, we learn how to use the techniques of geothermometry and barometry and calculate pressure and temperature values very accurately using proper geothermometers and barometers. We have to find our own system. We have to get our own thermometers and barometers according to our choices and get the values. We have to check and recheck our values for the values we are getting using these different programs, and we have to be very careful about the results we are getting, the pitfalls and the problems of each method we are using. So, manually you have to check all the errors should be calculated before using those values in our research or in our results. Nowadays the rigorous usage of geothermometry and barometry become very easy using the computation techniques and made to easy softwares. These softwares are getting us very good results, very reliable results, but one has to understand the science behind the writing these softwares and how this software is actually working. This is particularly useful for phase diagram modeling, where the system may ask you some questions. Unless you know those answers, you can formulate a diagram with very good pressure temperature PT paths, but those could be erroneous unless the basic science behind those phase diagram modeling are not taken care of. And before commenting on the nature of pressure temperature path or PT paths, whether this is a clockwise path or anti-clockwise path, without proper understanding of the different segments of this PT path, if we do the tectonic interpretation based on these rocks, these can lead to very erroneous and disastrous results. So, you have to be very careful about using your data. This is a very fantastic methods, you can use it and you can get the things running, but you have to take care of the pitfalls and what are the different possible errors that can lead to our results. So, you have to be very careful. So, thank you very much for your attention.